Good evening, students. Am I audible to you all?
Yes, sir.
Yes,
Good
sir.
evening.
Yes, sir. Thank you. So, on behalf of IGNO Regional Center Bhubaneswar, I welcome you all to the fifth day of our PGDSC theory class of your paper MCH-002. And from last 4 days or 4 classes, we have discussed different types of separation techniques, whether it is physical, chemical, or chromatographical. And as chromatographic separation technique is widely accepted and used for its simple technique, economic. So the chromatography technique we have discussed various types such as liquid chromatography followed by your gas chromatography, then high performance liquid chromatography is there, and today we will move one step ahead, that we will touch ion exchange chromatography and size exclusion chromatography, and the remaining part of HPLC, what we have left yesterday, will be discussed at the end of today's class, or we'll discuss it later. So uh, the new day, so a new unit must be started from our side, and let's have the discussion on your unit 9, that is ion exchange chromatography. I am sharing my screen with you now. Just wait. Yes. So I think the PDF is very much clear to all of you. Anyone? Is it visible clearly?
Yes, sir.
Okay, thank you. So in unit 9 of your postgraduate diploma in analytical chemistry, paper 2, it is ion exchange chromatography. So from its name, it is very much clear that some ions in the stationary or mobile phase get exchanged with the ions in the sample. That means this chromatography is mostly or generally can be used for ionic samples, where different ions are produced with some ionization mechanism or processes, and the stationary phase, which is mainly made up of some resins, that it may be artificial or natural, or that is synthetic or natural type. These resins having the ion exchange resin, we must say that it is ion exchange resin, and that resin will exchange the ions, whether it is positive ion cation or negative ion anion, with the sample, and it will be separated accordingly. So for this unit, I have one PowerPoint presentation is there. This is the PowerPoint presentation, that is ion exchange chromatography unit 9. Your program is postgraduate diploma in analytical chemistry, paper is MCH-02. It is in block 4, and it is today's date. So ion exchange chromatography. So amongst various separation technique, ion exchange chromatography or ion exchange is the most popular one, as this chromatographic process involved in softening of water. So what do you mean by softening of water? So as far as chemistry is concerned, related to water, Water is of two types, that is hard water and soft water. So what is hard water and what is soft water? Hard water is nothing but the water that contain carbonates of calcium, magnesium ions. That if the water contains some salts like carbonate salts of calcium or magnesium, etc., that water that water is known as hard water. And if you use the hard water for your soaping purpose or cleaning purpose, then your cleaning will be not be better because the water is hard, and that hard water will can be softened by using ion exchange chromatographic application. So by using this chromatographic method, the hard water becomes soft by exchanging the carbonate salts of calcium and magnesium, etc. So this is a most popular process for softening of water. It is also unique in terms of versatility and historical developments. I am not going through that part. So this ion exchange is firmly established as a unit of operation. All over the world, numerous plants are in operation, accomplishing the tasks that range from the recovery of metal from industries or industrial waste, and separation of rare earth elements also. So this is just a brief idea on ion exchange chromatography. So what is the introduction part? Ion exchange chromatography may be defined as the reversible exchange of ions. That means the exchange here, that is the mainly the ion exchange resin. It may be cation or anionic resin, depending upon the sample to be separated or the components in a mixture to be separated. This this is a reversible exchange of ions in the solution with ions that is electrostatically bound to some sort of insoluble matrix or a stationary phase. So here one reversible exchange of ions will be there in the solution, and that is bound to some sort of insoluble matrix. That is nothing but our stationary phase. So the stationary phase in your ion exchange chromatography is made up of a inert resin that is mostly insoluble, and it will not react with the sample or the solvent we use for the separation. This technique is extremely useful in the separation of charged compound. Charged compound means it is, we can say it is ionic compound, like protein differing by one charged amino acids. Generally, biological samples or pharmaceutical samples gets separated by using this technique. The ion exchange chromatography technique, one can choose whether to bind the substance of interest and allow the contamination to pass through the column and vice versa. So this is another property of your ion exchange chromatography technique. The technique has been developed in 19th century, which was fastly used for purifying drinking water. Anisometry is a distinct principle of chromatography. Then we have, this is different types of commercial and lab type ion exchange reagents, which are, or ion exchange chromatographic instruments which are available in market. So this is just a traditional way, that is the laboratory type, and this is commercial type. This is very much inbuilt type mechanism, that everything is there in the inside this ion exchange chromatographic apparatus, and we have some sophisticated apparatus or instruments are there for ionic ion exchange chromatography. What is the principle involved? Ionization chromatography relies on the attraction between oppositely charged stationary phase known as an ion exchanger and analyte. That here there is electrostatic, or we can say it is oppositely charged attraction between the stationary phase. This stationary phase is nothing but that resin. That resin with the sample, that is nothing but our analyte. The ion exchanger consists of an inert support medium coupled covalently to positive, that is anion exchanger, or negative, that is cation exchanger functional groups. Then here we must understood that the medium, that is the resin, that is inert support medium, means it is the resin part which is nothing but our stationary phase. So here the inert support medium, that is the resin, if the resin is positively charged, that means it will attract the negative part of the sample. That means the positive part of the resin is known as anion exchanger, while if the resin's negative part, that will attract the positive part of the sample, so negative part will be the cation exchanger functional groups. So here the, as the oppositely charged ions attract each other, so the positive part is known as anion exchanger, but the negative part is known as the cation exchanger. To these covalently bound functional groups, the oppositely charged ions are bounded, that is the mobile counter ion, which will be exchanged with like charge ion in the sample having charge magnitude more than the ion bound to the matrix. That means here what happened, the charge particle of the sample will bound to the matrix with opposite charges. Thus, if anion exchange chromatography is performed, if anion exchange chromatography means it is the positive part, the negatively charged sample component will interact. That means the anion exchange chromatography means it is the positive part of the resin. If the positive part of the resin is applied, or is used, then the negative charge of the component will be interact with the stationary phase and will exchange for like charges, like charge ion already bound to the matrix. So these things are there, that if uh, not if the stationary phase is a positively charged resin, it is treated as anion exchanger, while if it is a negative one, then it is treated as the cation exchanger. This is the working mechanism or working principle of your ion exchange chromatography. That in ion exchange chromatography, let us, our cation exchanger is E minus Y plus, this is the resin, that is the stationary phase, and X plus is our sample cation, that is our sample contain cation as X plus. So consider a column having E minus Y plus cation exchanger, in which E minus is negatively charged exchanger and Y plus is the mobile counter ion, or it is the positively charged exchanger. Then what happen, if X plus is added to this resin or the exchanger, what happen, this X plus will attracted by the E minus, so a new type of compound, or we can say a interaction will develop, that is nothing but E minus X plus, and this Y plus will separated out. So this is just exchange of your Y plus in place of X, exchange of X plus in place of Y plus. This is nothing but the type of displacement reaction. The desired bounded cation X plus can now be eluted by either of the two methods. So this X plus can be separated or can be sieved by either of the two methods, that we may uh, we may treat this E minus X plus with a metal ion with higher magnitude of cation, positive charge, then this X plus will easily removed or separated, or by changing the pH of the solvent, this X plus can be separated. So first the Y plus of our resin is exchanged with X plus. Then after the displacement or the exchange process is done, this X plus can be separated by two methods. Number one is by using one higher positive charge ion, let it be M plus, or we may change the pH of the solvent to separate the X plus of the sample. Now this is the diagrammatic representation, that is E minus Y plus. This is the stationary phase or the resin, or that is the positively charged resin. Okay, so here what happened, the X plus, that is the sample ion. If X plus is a sample ion will be there, then Y plus of the resin will be displaced by X plus. So we will have the interaction between E minus X plus and Y plus will be separated out. So this is also done uh, with the mechanism of your adsorption. Again, there is a in electrostatic interaction is there, but after the adsorption this interaction develop. So this is nothing but your displacement reaction type. So working principle, there are four steps, that is equilibration, sample application and washing, illusion and regeneration. This is equilibration. Equilibration is nothing but equilibrium type. The first step is the equilibration of the stationary phase to the desired starting point, start condition. When equilibrium is reached, all stationary phase charge groups are associated with exchangeable counterions such as chloride or sodium, as shown by blue counter ion and a red stationary phase, that is charged ion. So here what happened, this surface is the resin surface with positive and negative ions are there, and when the counter ion from the sample is just mm, uh, just present at the vicinity of this resin, then what happen, there will be equilibration will happening, and there will be exchange will occur. Then sample application washing, washing means this is application of water. So this is triatomic, that means it is water. So by application of water, what happen, the unwanted or unbounded materials get separated with the solvent which is used for the washing purpose, and finally this negative ion from the sample will interact with the positive resin. And also the sample buffer should have the same pH and ionic strength as the starting buffer in order to bind all appropriately charged proteins. Then ion exchange chromatography illusion will be there. So in third step, illusion biomolecules are released from the ion exchanger by change in the buffer composition. A common way is to increase the ionic strength with sodium chloride or another salt in order to desert the bound protein. Proteins are deserted relative to the number of charged group on their surface. So these proteins or the positive and negative ions which are get interacted are on the surface, and then from the surface this may be dissolved, that is detachment of the sample from the surface of the resin will happen, and this depends on the number of charge group that is on the surface of the resin. So these are some amino acids example with their ion exchange chromatographic peaks, and this is a detector signal with time. This is aspartic acid, threonine, serine, glutamic acid. So this is collected from your 2007 Thomson Higher Education book. So this is one example of your ion exchange chromatographic peak is there. So what are the basic requirements to have a setup of ion exchange chromatography. The first one is the column, that is the your stationary phase. So the stationary phase, which is made up of resin, or it is made up of some polymer or glass or stainless steel. So this is the column. Sorry, this is the column. That is the outer part. This is the, or this is the, these materials are used to prepare the column. And how the column is packed? It is packed with wet packing method. The wet packing means it is preparation of a slurry of the eluent with the stationary phase powder and then carefully poured into the column. Care must be taken to avoid air bubbles. So a slurry is prepared with the solvent or the eluent with the stationary phase powder is there. The stationary phase powder, it may be silica gel or SiO2, or it may be alumina, it may be activated charcoal, or it may be depend on your sample to be separated. The stationary phase is accordingly selected. Then application of the sample, then after preparation of the packing, the sample is introduced into the chamber or the column. So after packing, the sample is added at the top of the stationary phase using micro syringes or pipette. The same mechanism is also applied to your liquid chromatography and gas chromatography. So the sample is introduced into the stationary phase from the top side. This layer is usually topped with a smaller layer of sand or with cotton or glass wool to protect the shape of the organic layer from the velocity of newly added eluent. So there will be application of sand with cotton or glass wool will be there for the protection of the organic layer. Then, what are the different mobile phases used for this purpose? This may be acid, alkali, or buffer, depending on the type of sample to be separated. That is, if it is, it may be acid, it may be alkali, it may be buffer. Then, what is the stationary phase? The ionic compound consisting of cation species and the anionic species B minus. What are the illusion? So component of the mixture to be separated and moved down the column at a different rate depending upon their affinity with the ion for ion exchanger. The eluates are collected at different stages. So uh, there will be movement of the eluent or the movement of the solvent from top to bottom, that is above to below direction, that is with alignment to the your gravitational force of attraction, that is from top to bottom. And depending upon the affinity of these different components in the mixture to the resin, that is ion exchanger or ion exchange resin, the different components get separated and eluted accordingly at a different stages. Then the eluates, after separation, the eluates or the components are analyzed using spectrophotometric method. It may involve your UV visible spectroscopy, IR spectroscopy, NMR spectroscopy, C13X, C13 NMR, H1 NMR, different type of NMR spectroscopy are there, or mass spectrometry is there, or we have flame photometry for polarographic experiment, or conductometric type for conductance measurement. Then this is one example of your ion exchange chromatography, where this is the resin or the stationary phase, and here at the top of the resin the sample is introduced, and we have the separation after the exchange of the ions. The sample, the different components get separated on the basis of their retention factor or their affinity towards the stationary phase. So this sample is now separated into three colors. That means three components are present here. that is red is at the bottom. That means red has the weak affinity or weak attraction towards the stationary phase, and maximum attraction with the mobile phase. So that's why this is separated first, followed by this blue color one is there, and the last one will be the this is the gray color, and this is the blue color component. So we have three components are here. So this separation undergoes the exchange of ions, that is the exchange between the ion present in the resin or the stationary phase with the ion present in the sample. What are the different factors which influence the ion exchange separation? Ion exchange resin, this is the number one factor. The resin, that is the stationary phase. The swelling factor or and cross linking is important for the effective separation. If the resin is swelled or there is cross linking of the resin is there, then it will badly hamper the separation technique, that is the ion exchange technique. The cross link should be controlled as it affects the exchanger capacity. If the resin is cross linked, what happens? This becomes a bigger molecule, and there will be not uniform pores will be there, so the ion exchange will not be symmetrical. So that's why the ion exchange capacity will reduce. The swelling helps in proper exposure of charged functional groups for exchange of ions. Swell-less separation of ions of different sizes is difficult. This is the simple one, that if the swelling is less, then different size components will be affected. Nature of exchange ions, valency of ions, size of ions, polarizability, concentration of solution, concentration and charge of ions. So these are the five factors or five things under your nature of exchange ions. Then we have pH of the mobile phase, that is the solvent or the eluent we are using for your separation. Ionic strength is there, mobile phase modifiers are there, then temperature, and at the end we have the buffer. So the buffer is to maintain the pH, the constant pH. As we know, buffer is the solution which pH doesn't change by addition of little amount of acid, water or alkali to it. That means the by using the buffer solution, the pH of the experiment or pH of the analysis is maintained. The pH of the buffer should impact the same charge to the sample ion as present in the column. Ion exchange chromatography should be carried out with cationic buffer and vice versa, because buffer ion will indulge in ion exchange, which will be of no use. So buffer plays an important role in separation. So what are the ion exchangers? These are of three classes, that is resin type, gel type or inorganic exchanger. The first one is resins. Ion exchange resins are used for the separation of small molecules. Gels are used for the separation of large molecules like protein and nucleic acid. And inorganic exchangers, these involve harsh chemical condition, that is high temperature, high radiation level, strongly basic solution of powerful oxidizing agent, employing inorganic ion exchanger, etc. So these are the three types of ion exchanger which are mostly used as stationary phase in ion exchange chromatography. Then if I go for the first type, that is ion exchange resin, then it is again of various types. That these are strongly acidic, weakly acidic, strongly basic, weakly basic. So these are of four types. So under strongly acidic we have sulfonic acid, group attached to styrene and divinyl benzene copolymer. That means it is a resin which contain sulfonic acid, that is alkyl group containing SO3H. It is the functional group formula of your sulfonic acid, that is SO3H. If you see, SO3H is attached to just wait. So then we have that is resin. Ion exchange resin is primarily of four types. That is, it may be strongly acidic, weakly acidic, strongly basic, and weakly basic. So the example of your strongly acidic cation exchanger uh, is your sulfonic acid group, that alkyl group containing SO3H functional group, that is attached to styrene. Styrene is nothing but a benzene containing CH11CH2 and divinyl benzene copolymers. So these are used as cationic exchanger as strongly acidic one. Under weakly acidic cation, we have carboxylic acid group attached to acrylic and diphenyl benzene copolymer. We will go through all the structures. Then strongly basic anion exchanger. So when the anion is there, that means the medium becomes strongly basic. That is, basic means it is quaternary ammonium salt or group that attached to styrene and divinyl benzene copolymer. And for a weakly basic anion exchanger, we have polyalkyl amine groups. Then according to the source, that is a natural resin. If it is cation, it is zeolite and clay. If it is anion, it is dolomite. For synthetic resin, it may be inorganic or organic type. For organic resin, these are the polymeric resin matrices. So these resins are generally amorphous particles. So amorphous means it is fine powder type particle. They are not uniformly uh, distributed, or we can say these are of disordered manner of arrangement of particles. Polystyrene resin for ion exchange are made by copolymerization of styrene and divinyl benzene. Dimethyl benzene content is varied from 1 to 16% to increase the extent of cross-linking. Benzene groups are modified to produce cation exchange resin and anion exchange resin. Resin made from both these materials differ in their flow property, ion accessibility, and chemical and mechanical stability is there. Selection of one or other type of resin is done on the basis of compounds being separated. So this is just some points related to your ion exchange reagent. So here the chemical structure or the chemical formula is there. So this is nothing but your styrene, that benzene ring containing CH double bond CH2. Then if it is divinyl benzene, so this is divinyl means it is vinyl group means it is CH double bond CH2. So this is at para position. So this is divinyl benzene. Then when the styrene treated with divinyl benzene react with divinyl benzene, then we have a cross linked type of resin which is very much used as an cationic resin. Ion exchange gels, cellulose and dextran ion exchanger, which are polymer of the sugar glucose, possesses large pore size and low charge density because they are much softer than polystyrene resin. Dextran and its relatives are called gels. So just see these things that for the ion exchange gels, before that this is ion exchange resin, this is ion exchange gel. For the ion exchange gel, the material used are cellulose, dextran, ion exchanger, these things are there. So these are mainly used for the ion exchange chromatography purposes or for the softening of the water. So this is the cellulose structure. It is a high molecular weight compound which can be readily obtained in a pure state. Cellulose has much greater permeability to macromolecules. So macromolecules or big size molecules may be permeated or has higher permeability through glucose. So this is can be used as gel. Then we have exchange medium. So the choice of ion exchange depends upon the stability, molecular weight, and ionic strength of the sample component. The volume of the exchanger used for separation is usually 2.5 fold greater than to exchange with the ion in the sample. The ion exchanger are packed in column having suitable buffer. It is again of two types, that is cation exchanger and anion exchanger. So this is a medium. So this is the anion exchanger. Uh, have positively charged exchanger with negatively charged mobile counter ion available for exchange. That means anion exchangers have positive charge exchangers with negatively charged mobile counter ions available for exchange. That means negative ions are there for the exchange and positive ions are, we can say this is the static one and this is the mobile one. So positive ions are static ions and negative ions are mobile ions. So mobile ions, the mobile negative ions get exchanged with the positive part of the sample. So that's why this is anion exchanger. And here just see this is a positive part exchanger, mobile counter ion, and this is ion exchange resin. So the if the basic functional groups are introduced, the resin becomes anion exchanger. That is tertiary amine, strong anion exchanger, secondary amine, weak anion exchanger. So Just you should remember these examples. That is, if tertiary amine is used, then strong anion exchanger. Then this is a strong anion exchanger. If secondary amine is used, that is less one amine is less in secondary amines. So this becomes weak. That is, the donation of the electron become less. Then we have some example, that is strong anion exchanger have three methyl groups or three ethyl groups, but in a weak we have two ethyl groups or one amine group here. So this is in short, this is CH2N plus CH3 whole thrice. This is trimethyl aminoethyl and this is triethyl aminoethyl. So in short, it is TAM and TEAE. So the weak anion exchanger we have aminoethyl, that is C2H4N plus H3, and we have a diethyl aminoethyl. So this is DEA. This is weak, and here the number of ethyl group is less than the strong one. So ethyl and methyl groups are electron donating groups, which donate electron to nitrogen and which can be say so the this becomes the strong anion exchanger type. Strong cation we have sulfide, that is SO3 minus. In coordination chemistry it is named as sulfo. Then CH2SO3 minus, this is sulfomethyl. In weak cation exchanger type we have CH2CO minus, this is nothing but your aceto or carboxy methyl. So these are some examples of your anion and cation exchanger. What are the different advantages of your ion exchange chromatography? This is cost effective because the resin is very economic, and the resin can be reusable, easily collectible also. Low maintenance cost is there, efficient technology, and quick separation occur. Then the applications are softening of hard water, demineralization of water, to analyze base composition of nucleic acid, to concentrate the metal ion in the sample, to measure the additive in food and drug samples, to separate protein mixtures, for extraction of enzyme from tissues, purification of uh, solution free from ionic impurities, separation of inorganic ions, separation of sugar, amino acid, and proteins. Then at the end, it may be used as column in high performance liquid chromatography. So let's have our PDF, what left in our PowerPoint presentation. So this is the introduction part. Just see, this is the general mechanism, that when a sodium salt is treated with calcium salt, then calcium halide, that is NaCH2 is there and 2 NaCl. So here just positive and negative ion gets exchanged. So this is cation exchange reaction, that is Na plus is replaced by calcium, and here also this is an anion exchange, that is chlorine is replaced by sulfate, that is H2SO4 plus 2 NaCl. So this is the general chemical reactions are there, and this emerges out. A useful exchanger must have the following requisites. It should have negligible solubility in the medium. It must contain sufficient number of accessible ion exchange groups, and it must be chemically stable. It should be sufficiently hydrophilic, that is attraction for water, to permit diffusion of ion through the structure at a finite and usable rate. If it is hydrophilic, that means in presence of the dielectric constant becomes higher and the separation or the ionization of the sample becomes easier. The swollen exchanger must be denser than water. These things are there in classification of exchanger already discussed. We have some geolites, some minerals like analcite, chabazite, naturalite. This formula is there. These are can be used as the natural exchanger. Then in synthetic, we have the carrier ionic groups like SO3 minus, that is sulfide, carboxylate, phosphite, or for anion exchanger, we have NH3 plus, NH2, N plus. These are the carrier groups. So here the NH3 plus is having the high affinity for your anion, so that is greater than NH2, which is greater than N plus. Then we have liquid ion exchanger is there, that is high molecular weight amine or quaternary ammonium salts behaves as liquid anion exchangers. And this is in liquid state. Then you have synthetic exchange resin. So in synthetic means this is artificial. Sorry, this is synthesis of ion exchange resin. Sorry. So how to synthesize different ion exchange resins? We have cation exchanger. That it may be condensation polymerization or addition polymerization. So in condensation polymerization, what happens? That there is condensation of monomers are there with removal of some byproducts. So here what happened? The phenol. This is the phenol undergoes sulfonation. This is in terms of sulfuric acid means this is sulfonation to give this is sulfonic acid. Okay, this is sulfonic acid which react with H2CO group to give the resin. And similarly, this is a condensation polymerization process, and we have also addition polymerization is there, which is already depicted in our PowerPoint presentation. That when styrene react with diphenyl benzene, one copolymer is produced, or this is the final product is the sulfonic acid. That is, this copolymer undergoes sulfonation, that is react with H2SO4 to give the sulfonic acid derivative. Similarly, the ion exchanger, this is the amine, and this is the quaternary amine, and this is the tertiary amine. And these are some examples of the anion exchanger. Similarly, phosphorus can be used and sulfur can be used. And for these, we may have the same mechanism, that is condensation and addition. In condensation, we have 1,3-diaminobenzene or meta-amine aniline react with formic acid, that is sorry formaldehyde, to give this to give this anion exchange resin. Similarly, for addition polymerization, we have the example of this one. This is quaternary ammonium group are strong bases, and those with amino or substituted amine groups show weakly basic property. Then we have amphoteric one. This is neither positive, neither acid nor basic. This is known as amphoteric. For amphoteric, we have the styrene reacts with vinyl chloride in presence of divinyl benzene. We have the reaction of this one, which treated with trimethylamine to give product this, which undergoes sulfonation to give the product this. That means, I remember the sulfonic acid group, that is the SO3H, is attached to the ion exchange resins, which are used for better separation. Then we have trade names. This is very important. This is a manufacturer, this is a trade name. So under this trade name, different resins are different ion exchange resins are available in market. Then we have Dow Chemical Company USA, the trade name is Dowex. Rome and Hash Company US, the Umber Light. This is again chemical process, this is Duolite. This is bear forben. This is leolite. So this type of things are there. Then we have the nomenclature. The type, that is DOX 50, 50W cation exchanger, DOX 12421K anion exchanger. Here X number or percent divinyl benzene like X8, mesh size 20 to 50, and it forms sodium. The label will carry something like this: type 50, percentage X8, mesh size 20 to 50, and further these are the company trademarks for their product. Then these are some resin properties. It must be moisture content, particle size, cross-linking capacity, distribution coefficient, efficiency of exchange, resin selectivity. Just go through these things. So these are some of the properties of your resin to be used as the stationary phase. Just what will be the temperature, what will be the moisture content, these things are written here. What is the particle size of the resin should have for better separation. Then we have cross-linking resins. What are the examples? Then what is the capacity of the benzene to separate different components in a mixture? Then we have distribution ratio, that is concentration of anion in the region by concentration of same ion in the solution. And this is known as distribution ratio. How much concentration of the anion is present in the resin and what is the total concentration of the same ion in the solution. In conventional unit, the distribution ratio is amount by kg of the dry resin by amount per liter of the solution. So this is the distribution ratio. The what amount of resin is used divided by what amount of solution is there. If I go for the graphical presentation, that is concentration of the ion in solution versus concentration of the same ion in resin, then this type of plot will be there. So this is capacity of maximum capacity of the resin. This is distribution isotherm, the limiting slope equal to d value. So this type of curve will be seen. So distribution ratio is amount per liter of wet volume by amount per liter of the solution. So this is the now this solute or this sample is converted into volume. So now D, the conversion factor D to dV. So in terms of volume is there. So then there is distribution coefficient is there. Concentration of 1 gram of the resin by concentration in 1 ml of the solution. That is, it becomes unit measurement per gram or per milliliter. This then equivalency of exchange, resin selectivity. So these things are there. Then we have types of functional group. This is in Dow X1, the strong anion exchanger. This is the formula. Then valency, if the valency of the positive ion is higher, then the exchange will be better. So the element or the atom with higher positive charge value, then their efficiency will increase. Then followed by, under similar condition, the if the ions have the same charge, the extent of exchange decrease with size of the hydrated cation. That means when the size is larger, then their efficiency is better. So lithium having the smallest size is having the smallest efficiency of extent of exchange, and silver plus Ag plus will have the highest one. Then in case of divalent ion, the same thing is there. With the strongly basic anion, the order of negative ions will be this one. Nature of non-exchange ions: ion form of resin, total solution, ionic strength. So ionic strength is nothing but your concentration of the ions. This will be the strength of your ions in your solution. So monovalent exchanges are usually little affected by the change in the total ionic strength. However, it becomes important if the exchanges are taking place in different valency, say monodivalent exchange. This is mono, that is sodium chloride, and this is RSO3S. So this will be exchange. So this becomes HCl plus sodium salt of sulfonic acid. So the ionic strength of the monovalent, that is Na plus and H plus, this will be like this. So these are their respective meanings. Just go through these things, and the same equation is here. Then we have at the last part operating method, we have batch operation and column operation is there. Just an exchange column with fraction collector. So this first component is collected drop wise, so this becomes a fraction type separation. Then we have moving bed operation. This is somewhat a different type of column operation is that encountered in a moving bed or continuous counter current system. That means the bed on which the component is separated is three-dimensional bed which is rotating, and the sample is uniformly separated. Ion exchange is mixed aqueous organic media. So these are some theory parts. Just go through these things. And we have specific cation exchangers are there. This is nothing but your dipicryl amine. The structure is like this. Then dipicryl amine, and this is your yes. So diprocalamine is known as specific precipitating agent for potassium ion. The resin is synthesized from polystyrene by nitration, reduction, condensation with picryl chloride, and again nitration. So this is the mechanism, organic reaction mechanism steps that the polystyrene area first undergo nitration. Nitration means it will have NO2 group, then followed by reduction, that NO2 is changed to NH2, then condensation will be there and with picryl chloride. So after that this compound is formed. Then other compounds are like your orthoaminophenol, anthracyclic acid, diacetic acid, metaphenyl diglycine. These things are can be prepared. Then we have Dowex A1 type gelatin resin. This is the structure. In synthetic inorganic, we have different type and the characteristics. They are hydrous oxide of polyvalent metals, insoluble acidic salt of polyvalent metals, salts of heteropolyacids, insoluble ferrocianides, synthetic aminosilicates, and then miscellaneous inorganic ion exchangers, synthetic apatites, and sulfides. So these are some examples. Just remember 2 to 3 examples. All the just remember the examples. Then insoluble ferrocianides of silver, zinc, cadmium, copper, nickel plus two. These things are there. Synthetic aluminosilicates. The following. This is again of three types: amorphous two-dimensional layered aluminosilicates and aluminosilicate with rigid three-dimensional structure. So these are all your ion exchange resins compounds, the compound which are used to prepare your stationary phase, that is the ion exchange resin. Miscellaneous inorganic exchanger will be there, that will be a calcium, strontium, barium, cadmium in presence of M, and in presence of X it will be phosphorus, arsenic, vanadium, chromium, etc. Then special property, radiation and thermal stability, unusual selectivity. Then some application, this is separation of metal ion and anion, separation of organics, separation of ionized and from non-ionized, separation of actinides element, then miscellaneous application. So here there are some examples of your applications. Just go through these things. Try to remember one or maximum of two examples. Separation of actinides. So how actinides elements can be separated using ion exchange chromatography. It was developed by Glenn T. Seaborg using ion exchange equipment to identify 5F series beyond any doubt by the sequence of their appearance. Then miscellaneous application at the end. The separation by filtration or decantation, reduction of cost because the catalyst can be used repeatedly, using without regeneration, increased product yield and efficiency. At the end, the elimination of corrosion problem. Then after this, we will move forward to your next unit, that is size exclusion chromatography, which is nothing but your depending on different size or the pores of the stationary phase used, that is in terms of gel or in terms of solid. This will these things we will discuss in this part. And for this part also I have one PowerPoint presentation. So let's have a 5 minute break, and after the after 5 minutes we will again reunite. So till then, let's have some refreshment, then we will meet again. So welcome back, students. Now it is unit 10, that is size exclusion chromatography. So this is in your same block 4 of your MCH-2 paper of PGDSE program. Then these are the contents. There is introduction, principal, material, instrumentation, advantages, disadvantages, then application of gel electrophoresis size exclusion chromatography. So size exclusion chromatography, or SEC, also called size, is also called gel filtration. So student, am I audible clearly or not? Am I audible? Okay. So the PPT is clearly visible now. Okay. So in the introduction part of size exclusion chromatography, it is also called gel filtration or gel permeation chromatography, which uses porous particle to separate molecules of different sizes. That means with different dimensions of the sample, it can be separated by using this method. That is, it is mostly, or it is depends on the size factor or the dimension factor. It is generally used to separate biological molecules and to determine molecular weight and molecular weight distribution of polymers. So this is also used specifically for biological molecules like your ion exchange chromatography, where protein amino acids are generally separated. It is usually applied to large molecules or macromolecules complexes such as protein, industrial polymers, etc. When an aqueous solution is used to transport the sample through a column, the technique is called gel filtration. When when an aqueous solution is used, it is known as gel filtration chromatography, and when organic solvent is used, it is called as gel permeation chromatography. And here we just remember, we should remember that this aqueous solution, organic solvent, these are used as the mobile phase. When the mobile phase is water, this is known as gel permeation filter. Hello, କୁହନ୍ତୁ। So when aqueous solution is used as the mobile phase, ଅଧଘଣ୍ଟା ପରେ, then this is called gel filtration chromatography. When organic solvent is used, this is known as gel permeation chromatography. The separation molecule is called fractionation. Fractionation. Size of pores in beads determine the exclusion limit. What goes through the bead and what goes around the bead. This is very important. That is exclusion limit. So that's why this is known as size exclusion. That it will exclude the oversized particles, and it is only include the size that is easily adjusted with the pores of the beads. These pores of the beads are nothing but your stationary phase. So the size of the pores of the beads in the stationary phase exclude the oversized samples or components of the mixture, and it only include the appropriate size that will be adjusted with the pores of the beads used as the stationary phase. So here three things are there. When aqueous solution is used in the as the mobile phase, it is known as gel filtration. When organic solvent is used as the mobile phase, it is gel permeation. And here the oversized sample is excluded. That's why this is size exclusion principle. What is the principle involved? A mixture of molecule dissolved in liquid is applied to a chromatography column which contain a solid support in the form of microscopic spheres or beads. Then here the stationary phase or the chromatography column is packed with microscopic spheres or beads, just like the gel balls, the children play. The children are playing the with the gel balls, like that. Um, we have some spears or beads are used as the stationary phase in the chromatography column. The mass of bead within the column is often referred to as the column bed. So the column bed is nothing but the mass of the bead that is used. The beads act such traps or sieves. Sieves means it is just like the um, what is that in the preparation of a tea, the sieve is used for the separation of the tea from the tree seeds. The bead acts as the traps or sieves and function to filter small molecules which become temporarily trapped within the pores. So small molecules gets trapped within the pore of the beads, and the big size molecules will be separated first, because this will not be trapped. Larger molecule passed around and are excluded, and the smaller molecules are trapped by the pores of the beads. Large sample molecules cannot or can only partially penetrate the pore, whereas small molecules can access most or all pores. When the sample molecules are small in size, this will trapped by the pores of the beads or the stationary phase, and when the size of the sample is oversized, that is large size, then these molecules are excluded by the stationary phase. Thus large molecules elute fast. So as these large molecules are excluded, these are eluted fast, these are separated fast. Smaller molecule elute later, because these are trapped by the stationary phase, while molecules that can access all the pores elute last from the column. And there are molecules which are perfectly adjusted with the pore size of the stationary phase, and these perfect sized molecules are elute at the end of the column. The particle of different sizes with elute, that is filter, through a stationary phase at different rates. So uh, depending upon their different sizes and their adjustment with the different pores of the stationary phase, they are they are having different rates of separation. So this is the pictorial view, that this is the beads which are packed in the column, and this is the sample which is to be separated. It is just a mixture, and this is the zoom version or the of this small view. So this is the zoom view. Just see this one. These beads have some pores, and in these pores small molecules are perfectly trapped, but the large size molecules which cannot adjusted with these small size pores gets or find their way for separation. So these large size molecules will will elute fast or separate fast. Just see here, the small size are at the top of the column, the middle size are at the middle, and the large size are at the bottom. That means here the pores of the bead trapped the smallest or the small molecules of the sample, and they exclude the large size molecules. So this is, that's why this is known as size exclusion chromatography. So I just read this one. This is very small molecules enter many pores in the gel, equilibrating between the gel and the moving buffer, and so travel slowly and are elute at the end. So this small size that are colored violet, okay, violet or pink you may say. Then the blue color, this medium sized, the medium sized molecule enters some pore in the gel, equilibrating between the gel and the moving buffer. And the large size, this large size molecule enter few pores in the gel and so travel rapidly and are elute sooner. So these bigger size or large size molecules will uh, filtered or will be separated first, followed by the middle sized, and which will followed by the small molecules of the mixture which get trapped by the pores of the gel. So there is a mathematical equation is there. Mathematical equation is there, that is total volume, that is column volume. Vt will be Vc plus Vi plus Vo. So Vg is the volume occupied by the packing. Vg is the volume occupied by the packing. Vi is the volumes of solvent in the pore, and Vo is the free solvent volume, similar to injected volume. So that is the mobile phase. So how much the mobile phase is injected, that is Vo or V0 you may say, this is the free one, and Vi is the volume of the solvent get in the pores, trapped in the pores, and Vg is the volume occupied in the packing. So this is your blue line is your VO, Vs will be your, sorry, this is your Vg, that is volume of the gel matrix, and this is pore volume, that will be the Vi. So these things are there. The components of a size exclusion chromatography: stationary phase, mobile phase, column, pump, and detector. So stationary phase is a semi-permeable porous bead with well-defined range of pore sizes. So these stationary phase is made up of some beads with having which having some definite range of pores, and which is a semi-permeable one that allow this solvent particle to pass through it. It is known as the semi-permeable. Beads are, it must be cross-linked polymer. Degree of cross-link is controlled carefully to yield different pore sizes. Degree of cross-linking is controlled carefully to yield different pore sizes. Smaller pores are used for rapid desalting of proteins or protein purification. Intermediate pores are used to separate relatively small proteins. So these are some applications depending on the size of the pore. And the size of the pore is carefully controlled by the help of degree of cross-linking. Very large pore size are used for purification of biological complexes. So we have stationary phase used for gel exclusion chromatography, that is dextran, which trade name is Cefadex TM, and polyacrylamide and dextran polyacrylamide, which is Cefacryl TM. Each is available with a variety of different range of pores size in the bead, permitting separation of macromolecules of different sizes. Just see in our PDF that dextran, Cefradx, everything is there. So this is the schematic diagram of your size exclusion chromatography. Then we have the composition. Yes, this one, dextran sephadex. So this is the chemical structure of your sephadex, which is just like a mono unit of your cellulose unit, which is cross-linked, and there is linking between carbon oxygen CH2 CHO CH2O C carbon here, the straight chain, and this will go on. This is the sephadex one, which is available is a free flowing powder like structure. And we have also dextran N dash methylene bisacrylamide gel. In short, it is cefacryl. The second one, the cefacryl, the structure is just like this. This is the structure of your cefacryl, which is used as the bead with different ports for at stationary phase in size exclusion chromatography. Then we have also polyacrylamide gel. In short, it is biogel. There is amide group. Amide group means it is CONH2 group. Amide group is there. That is CONH2 group is here. So amide linkage is there. So this is polyacryl amide gel, which is followed by agar and agarose gel, and this is a hexa atomic cross-linked structure like your sucrose, glucose, galactose. This type of molecules get cross-linked, and that is polysaccharides. And we have agar and agarose gel. Then we have styrene divinyl benzene gel. In short, it is styra gel. So the styrene gel formula is not here. So this is styrene and divinyl benzene. The styrene means it is benzene containing CH2, and divinyl benzene means it is benzene containing CCH2, and at the para position it is again CH2. So these are some examples of your sephadex, cephacryl, etc. Then we have a good stationary phase should have following property. So what are the different properties of a good stationary phase? That is the bead, which are used for the packaging of the column as the stationary phase. It should be chemically inert, inexpensive, not react with component to be separated, not react with the eluent, that is the mobile phase, should be colorless, uniform in size and shape, should be mechanically stable. So these are the six distinct properties, unique properties of a good stationary phase bead in size exclusion chromatography. Then soft gel, these are the examples. Soft gel, this is dextran, trade name is Cefadex. Polyacryl amide gel, that is used for separation of proteins. Then semi-rigid gels also there. Examples is biobeads. These are used for separation of non-polar polymers in non-polar solvents. Then highly rigid gels and glasses that are used for the separation of polar systems. This is the dextran, a homopolysaccharide of glucose residue. It is prepared with various degree of cross-linking to control pore sizes. It's brought as a dry bead. The beads swell when water is added. The trade name is Cefadex. It's mainly used for separation of small peptides and globular protein with small to average molecular masses. So this is your dextran, also known as Cefadex, which is a homopolysaccharide of glucose unit. And these are some exam applications, and their pore size is controlled by the degree of cross linking. and this is typical separation range that can be achieved using Cephatics are given below. Molecules ranging from 100 to 600,000 DA can be separated depending on the type of Cephatics chosen. This is the Cephatics version and this is the range. Polyacrylamide, these gels are prepared by cross-linking acrylamide and N-methylene bisacrylamide. The pore size is determined again by the degree of cross-linking. The separation property of the polyacrylamide gels are mainly the same as that of dextran. They are sold as Biogel P. It is a trade name. They are available in wide range of pore sizes. So depending on the application of the application, different pore sizes are available. Then agarose, this is linear polymers of D-galactose and a 3,6-anhydro-1-galactose. You have to remember this, these chemical names, that what chemical is used or what compound is used for the preparation of which type of bead. For agarose, it is D-galactose and 3,6-anhydro-1-galactose. It forms a gel that is held together with hydrogen bond. It dissolves in boiling water and forms a gel when it is cold. So when it is cold, it forms a gel-like structure or gel property. It shows, and when it is form a gel due to formation of the hydrogen bond. And in hot water, boiling water, it gets dissolved. The concentration of the material in the gel determines the pore size. The pore of the agarose gel are much larger than those of the Cephatics or Biogel P. So the pore size is larger than the first two. It is useful for analysis separation large globular protein or long linear molecules such as DNA. So these are the application part, that is analysis or separation of large globular protein or long linear molecule such as deoxyribonucleic acid, that is DNA. And after the stationary phase, we have the mobile phase. So mobile phase, the liquid used to dissolve the biomolecule to make the mobile phase is usually called a buffer. So in chemistry, we can say buffer is a solution which pH doesn't change after addition of little amount of acid, base or water to it. So buffer has a resistance of pH or a pH resistive solution, which pH is not changed by the application of acid, base or water to it. The mixture of biomolecules dissolved in the buffer is called the sample. The mixture of biomolecules dissolved in buffer is called the sample. The choice of mobile phase to be used in any separation will depend on the type of separation to be achieved and component to be separated. This depends on the type of compound to be separated and type of separation we wish to achieve. The most common element in the polymer that dissolve at room temperature are THF, that is tetrahydrofuran, chloroform, dimethylformamide, etc. So mobile phase for synthetic elastomers, polybutadiene, polyisoprene, the solvent is toluene, because these are all synthetic elastomers, so toluene will be the right solvent to be chosen. Then polystyrene, polyvinyl chloride, styrene butadiene, rubber, epoxy resin. For this type, tetrahydrofuran is the preferred solvent. Then polyolefins, for this trichlorobenzene is there, polyurethane, dimethyl formamide, protein, polysaccharides, water and buffer. Then it is the solvent selection. The solvent used for mobile phase of SEC are limited to those following the criteria. The solvent must dissolve the sample completely. Very important. Which solvent is used for to dissolve the sample? The solvent must dissolve the sample completely. The solvent has different property with solute in the elute, typically with solvent refractive index. Solvent must not degrade the sample during the use, otherwise the viscosity of the eluent will gradually increase over time. The solvent is not corrosive to any component of the equipment. So the solvent to be used must have these characteristics to be used in size exclusion chromatography. Mobile phase preparation. The solvent which is used to prepare the mobile phase must be in high purity, must have high purity. Filter mobile phase solvent using 0.5 micron filter to remove any particular impurity such as dust, insoluble salt. Antioxidant is added to trichlorobenzene to keep solvent stable in high temperature. So these are the precautions we must take to use the solvent as the mobile phase in size exclusion chromatography. Other additives eliminate absorption or interaction of solute with column packing materials, size exclusion chromatography. Then we have sample preparation. Sample solution are supposed to be prepared in dilute concentration that is less than 2 milligram per milliliter. A good solvent can dissolve a sample in any proportion in a range of temperature. Sample with a broad molecular weight distribution may require higher concentration. It is recommended to filter the sample solution before injecting into column in order to get rid of clogging and excessively high pressure problem. So these are some points related to the sample preparation, that how we can prepare our sample for size exclusion chromatography, that for a broad molecular weight distribution we require a higher concentration of the sample, and the solvent which is used to dissolve the sample must must be chosen like this, that the proportion of the sample should be uniform in wide range of temperature. Agitation and filtration. General filtration is required to remove insoluble impurities, and do not agitate or filter sample that contain very high molecular weight that is greater than 1 million. So these are some points related to your sample preparation. Then the column part is there. For commercially available column for your size exclusion chromatography, the analytical column is 7.5 to 8 millimeter in diameter. Preparative column, it is 22 to 25 millimeter. Usual column length, it is 25, 30, 50 and 60 centimeter length. The length of this column is like this. Recently, narrow bore column 2 to 3 millimeter diameter have been introduced, which save time and solve the problem. So these are some commercially available columns for your size exclusion chromatography with different dimensions. Shorter column save time and solvent. How to selection of column? So this is the shorter the column, the time saving is more, and the solvent is also a small amount of the solvent or volume of the solvent is used in case of shorter columns. Small particles provide a better resolution. If the particle size is small, then resolution will be better. On the other hand, 5 mm, even 3 millimeter packing are more sensitive towards contamination by sample containing impurities. Particles as large as 20 millimeter have been recommended for very high molecular weight polymers. There is some specification of your column separation selection. Small size particle packing can sometimes result in shear degradation of large polymer molecules because the space between particles is very narrow. The packing should be adjusted accordingly depending upon your size of the particle in your sample. Column with different porosity or mixed bed column provide a better separation. Column with different porosity or mixed bed column provide a better separation. How to handle size exclusion chromatography column? A column set in SEC should be always run in the same mobile phase. It must be isocratic, that is mobile phase is same. SEC column should never be operated in a backward direction, always from top to bottom. Care should also be taken in connecting column or in sample injection. When you inject your sample from top of the column, it must be added carefully. Replacing a clogged inlet. Replacing a clogged inlet. Just wait. Replacing a clogged inlet feed is a dangerous operation which can reduce column performance. If the inlet is clogged, then the performance will be reduced. A damaged or dirty check valve or pump can also reduce column life. So these things are there, and this is a size exclusion chromatography instrument having different apparatus like different parts like this is the mobile phase, that is the solvent, this is the injection valve, this is the column, and these are some uh, electronic connections are there. This is the recorder, and here it is the detector interface is there, and also a pump is there. A highly constant flow rate has to be maintained during the entire chromatogram. This is very important in size exclusion chromatography. A change of the flow rate of only 0.1% can cause an error in molar mass of up to 10%. The flow rate is changed by 0.1%, then error in the molar mass is up to 10%. So it is that much sensitive. Most pumps can only reproduce the flow rate of 0.2 to 0.3%. In line filters in the solvent reservoir may prevent particles from coming into the pump head, which might damage the check valve or the pump seal. The type is syringe pump and reciprocating pump. This is just some important points related to your pump. And the detector, the concentration sensitive detector, that is bulk property detector, we have refractive index detector. Solute property detector, we have UV. For evaporative detector, then we have ELST, evaporative light scattering detector. Molecular mass sensitive detector, so the components are detected in two manner, that is in concentration term and as well as in molecular mass, that is by weight term. If it is concentration, then the detectors are RI, that is refractive index, UV ultraviolet, and we have ELST, evaporative light scattering. For molecular mass, we have light scattering detector LST, low angle light scattering, and multi angle light scattering detector. So this detector name you should remember, which are used in size exclusion chromatography. Then we have viscosity detector for different differential viscometers. Other are like flame ionization detector, FID. We have Fourier transform, infrared, FTI are there, mass spectrometer is there. So there, these are some detectors which are connected to SCC, size exclusion chromatograph, for the detection of different sized components present in a mixture. So the advantages of this size exclusion chromatography is this is a short analysis time. This takes short analysis time, well defined separation, depending means it includes oversize exclusion. This is one of the good mechanism involved in this process. Narrow band and good sensitivity, no sample loss, small amount of mobile phase required. If the column is a very thin column, the flow rate can be set by adjusting the pressure in the pump. Further disadvantages: limited number of peak that can be resolved within the short time scale of the gel formation chromatography run. Filtrations must be performed before using the instrument to prevent dust and other particulates from running the column and interfering with the detector. Filtration must be done. The molecular mass of the most of the chains will be too close for the GPC or SCC separation to show anything more than broad peak. Then the application include protein fractionation, purification, molecular weight determination, separation of sugar, protein, peptide, rubber, and other on the basis of their sizes. This technique can determine the quaternary structure of the purified protein. Then size scale chromatography is a widely used technique for the purification analysis of synthetic and biological polymers such as protein, polysaccharide, and nucleic acid. Various species of ribonucleic acid and viruses have been purified using agarose gel, then desalting, then copolymerization studies. These also the applications. Then this is all about in our PowerPoint presentation. Let's have a look on our PDF. Your IGNO material variables depending the utility of the gel. What are the variables already discussed? Then unique features of the technique, that is size exclusion, some applications, analytical application, preparative application, and miscellaneous application. So under analytical application, we have analytical group separation, analytical fractionation. Then we have measurement of protein binding and complex formation. These are all include your biological uh, estimation, determination of molecular masses of the biological samples using carbohydrates, peptides, and the Sephadex G100, Sephadex G200 have been mostly used for preparative purpose. It is a group separation or fractionation. They go through these things. Then under miscellaneous, we have some miscellaneous applications are there. That is a separation of different biological samples including DNA fragments, oligonucleotides. They are significantly separated. Then we have the at last the separation part, summary part. So in broad sense, the ionisation chromatography and size exclusion chromatography, in both the chromatography, the in the mechanism of separation, ion exchange, the charge of the ions or charge of the different particle present in the component matters, and in size exclusion we have the dimension or the size which results in separation of the component from the mixture. So this is all about your unit 9 and unit 10. So now the platform is open now for discussion. So anything related to Unit 9 and 10 related to ion exchange chromatography or size exclusion chromatography. We will try to clarify your doubts. So now it is on you students to ask questions or anything you wish to add, because your these units will take minimum 4 to 5 classes to complete, but we have 7 classes for completion of 13 units. So for each day we have to complete 2 units. So broadly, you just if you understood the mechanism, the working principle, the different components or different parts of the chromatographic technique, then you can easily write whatever question came will come in your exam. So just remember, in chromatography, uh, what is the stationary phase and the mobile phase is used, number one. Number two, which process is adopted. For process means what mechanism or what working mechanism is applied to that particular chromatography. For example, in liquid solid chromatography, the adsorption phenomena is applied, but in liquid chromatography, partitioning phenomena is applied. So these things you just remember, and I think you will not face any difficulty in writing your answer in exam. So now it is on to you students to ask questions if you have, else we will wind up the session. So till now we have covered I think 5 to 6 chromatography techniques. That is liquid chromatography uh, is of two types, LSC and LLC. Then we have discussed HPLC also, high performance liquid chromatography. Then we have gas chromatography. Under gas chromatography, we have again GSC and GLC. Then we have discussed planar chromatography, that is two-dimensional, that is paper chromatography and thin layer chromatography. Today we have discussed ion exchange chromatography and size exclusion chromatography. And tomorrow we will have membranes, the separation involving membrane, that I already point out in my first class, that is reverse osmosis, which is a very popular phenomena in water purifiers. Reverse osmosis or membrane separation is there. This is number one. And we have in unit 12, we have electrophoresis, that is migration of ions to their respective electrodes. This include your electrolysis process mostly. That respective ions will flow to their respective electrodes. This is electrophoresis. Okay. So some large organic molecules or polymers will be there. You have to remember the formulas, and we have some pictorial or schematic diagrams are here, how the different ions migrate to their respective ends. So these things are there in our last unit. So if no questions is there, so we may wind up the session for today, and tomorrow we will have the next 2 units. Yes, Raut.
यस सर। सर एग्जाम पॉइंट ऑफ व्यू जो आप क्वेश्चन बोले ना सर, वो थोड़ा रिपीट करेंगे सर?
एग्जामिनेशन पॉइंट ऑफ व्यू से आप एक बात याद रखो, कोई भी क्रोमाटोग्राफी का क्वेश्चन आए एग्जाम में,
जी सर।
आपको आपको स्टेशनरी फेज, मोबाइल फेज एंड द मैकेनिज्म, व्हाट मैकेनिज्म इन्वॉल्व, ये तीनों अगर आप याद रख लोगे तो आपको क्रोमाटोग्राफी लिखने में कुछ प्रॉब्लम नहीं होगा। क्रोमाटोग्राफी में जो मैथमेटिकल पॉइंट ऑफ व्यू है और जो टेक्निकल पार्ट है वो है रिटेंशन फैक्टर और द एफिनिटी और द इंटरेक्शन ऑफ द sample to the stationary and the mobile phase. If you
ओके,
understood these things for a particular chromatography, then you can write in your own words.
ओके सर,
But okay, so this is just try to remember what chromatography is there, what are the stationary and mobile phases used, what is the mechanism, and what type of interaction, that is it is ionic interaction or it is size exclusion, or whether it is adsorption, whether it is partition, or whether it is like your TLC, it is also adsorption type. So these things are there. Okay,
यस सर, यस सर,
so
ओके सर, थैंक यू।
okay, in your WhatsApp group, I will share all the PPTs which we are using for these classes. So do not worry. And the day after tomorrow, the last day, I will share all the PPTs in your WhatsApp group. Okay.
ओके,
And the
ओके सर,
probable questions, if I have the last year examination last year, the if I have some soft copies, then I will also share in your group. Okay, and related to your practical classes, the regional center will decide what to do, and on the basis of that, we will have some classes in physical or in hybrid mode. So till then, so thank you to all for your patience hearing, and we will meet again at the same time and same platform. So thank you to all.
Thank you, sir.